This example is an example of using a series to figure out a formula for a recursion relationship. This is used in combinatorics, it's used in some decoding in computer science. We will not actually use this again, it's just showing you that series can be used for things other than the main things we've been doing in the course. So we're interested in a recursion relation, and we're going to start with a sequence of numbers, and we want that sequence of numbers to have the property that every number is the average of its neighbors. And so we're going to pick the first number, C0, and the second number, C1, and I'm calling them that just to match the typical constants for series. And we want that every number is the average of its left and right neighbors. So let's look at this. That gives us this. This implies this recursion relationship. If I solve this for Cn plus 1, multiplying both sides by 2, and subtracting Cn minus 1, I get this. And the idea about using series to figure out this recursion relationship is to create a function out of this sequence of coefficients using a variable x, and each coefficient is matched to the power of x, and we're now going to treat this function the way we would treat any function and manipulate it to try to understand what this function is, and from this function read what the coefficients are, and then we will figure out what these coefficients are for for any n. So rather than just starting with C0 and C1 and building up the sequence, we're actually going to be able to figure out what the 1,000,007th term is in the sequence. The relationship that we're investigating is this recursion relationship. The number, the n plus first number, is twice the nth number minus the n minus first number. We put these together as coefficients of a power series, and we are understanding what that function, what the properties of that function might be. Then we'll figure out what the function is, if it makes sense, and so on. We don't know what's going to happen yet. So let's look at the coefficient of xn plus 1 in the function. Cn plus 1 is, of course, the coefficient of xn plus 1 in the function itself. And then if I take x times the function, then Cn will be the coefficient of xn plus 1 in x times the function. And so 2x fx, the coefficient of xn plus 1 in this expression, will be 2Cn. And if I multiply f of x by x squared, then the coefficient, again, the coefficient of xn plus 1 is going to be Cn minus 1, right? Because f of x has Cn minus 1 multiplying x to the n minus 1. And when we bump the power up by 2, we will get Cn minus 1 multiplying xn plus 1. Okay, that's fine. This recursion holds for n bigger than or equal to 1. Now what happens for the lower powers? If we're looking at the constants, then the coefficient of x to the 0 here is going to be C0. The coefficient of x to the 0 here will be 0, because we've bumped everything up by x. And the same is true here, because we bumped everything up by x squared. And so we need to add C0 to the right-hand side of this equation for x0. And for x to the 1, again, we're talking about the coefficient of x to the 1 as opposed to x to the 2, 3, etc. On the left, we have C1 times x. Over here, we've multiplied f by 2x, so we have 2x times C0 is what we've got for x to the 1. Over here, we've multiplied by x squared, so we don't have any x to the 1 terms. And so looking at this, we need to subtract 2c0x, and we have to add c1x to make this equality hold. And so putting this all together, for higher powers of x, we have f of x is equal to 2x f of x minus x squared f of x. And to fix the first two, we have to add c0, and we have to add c1 minus 2c0x. And then this equality holds in general for this function f. We've checked it for all powers of x, and so it's correct. Collecting together all the coefficients of f of x, right? We had f of x, and then we had some multiples of f of x on the other side. Bringing all the multiples of f of x to the left here, and keeping the terms that did not involve f of x on the right. We have this 1 minus 2x plus x squared, you would recognize as 1 minus x squared times f of x, is equal to this linear function. And so f of x is equal to 1 over 1 minus x squared times this. Notice, of course, we're making the assumption that this all makes sense. So, for example, obviously x is not 1, or else this doesn't make any sense. And so we're proceeding formally. And again, we have seen 1 over 1 minus x squared in our experience with series as the sum, with the index going from 1 to infinity, of the index times x to the index minus 1, right? So this starts out with 1, and then the second term is 2x, and so on. And that is still multiplying this linear function. So let's see, for constants, we have the case where m is equal to 1. So we have 1 times x to the 0 times c0. And that's the only thing where we have a power of 0. We also have c0 multiplying all the other powers, and this is what we get. So if you want the relationship between m and k, k here is m minus 1. It's the power. And so m is k plus 1. And then multiplying the term that does have a power of x raises the power of x over here. So we have c1 minus 2c0 times x to the k. And again, k here now is x to the m minus 1 times x gives x to the m. So here k is equal to m, and the coefficient is k. So m here is k. And so that's what we're finding for f of x. Let's see what that means when we collect the powers together, right? We have here k starts at 0, here k starts at 1, but for k 1 or larger, we'll have terms from both of these sums. So let's collect them all together. We found that f of x, in terms of the coefficients c0 and c1 that we started out with, was this power series. Notice, by the way, that we still don't know a lot about the coefficients, but we do know that these both converge for x smaller than 1 in absolute value, because the radius of convergence for this series is 1, and the radius of convergence for this series is also 1, right? c0 and c1 minus 2c0 are constants. The coefficients, the dependence on k, the ratio in both of these will go to 1 times the absolute value of x. And so with that in mind, let's go see what we've found. If k is 0, then the only term here is 1 times c0, and that is, in this series, of course, for f of x, the first term is c0, and so this just says that c0 is equal to c0, which is fine. For x equal to, for the power equal to 1, just x, the coefficient of x, here the coefficient is c1. Over here, that corresponds to k equal to 1, so we have 2C0, and then over here we have 1 times C1 minus 2C0, and indeed, if you put this together, the C0s cancel, and this is just saying that C1 is equal to C1, and so that's correct. Now, what happens when k is bigger than or equal to 2? Over here we have ck, and in this sum, again, the coefficient of x to the k is k plus 1 C0 here, and k times C1 minus 2 C0 here. And so putting that together, we have k C0 minus 2k C0. So we have minus k C0. We have 1 times C0, so that's plus 1 times C0. And then for C1, we have k times C1. And so that's the formula that we found, is that the ckth number in the sequence is k times C1 minus k minus 1 times C0 in terms of the first two coefficients, C0 and C1. Now that we have a formula, you could actually check fairly quickly that it's true if you take the sum of Cn minus 1 and Cn plus 1. You'll see that you'll actually getting 2 times the value for Cn for every one of the choices of n that you want. And so now that we know the result, it's actually pretty easy to check that it's correct.